Hello kids, today I'm going to be reviewing the first topic from the block of general physics, in which we have the first unit as measurement, which is further divided into subtopics of length, volume, density, time, and lastly we will be looking into accuracy and precision of other measurements. So length, right? So what is length? Let's review this. So when we talk about length, we need to understand that length is actually a distance between 2 points. Let's say what is length? So length is actually, let's say if you have a point A over here and the point B over here, so the distance between these 2 points is what we call as length, right? And to measure this length, we have several ways to do this. We can use a ruler, right? We can make any other standard. Let's say I take a piece of block and then I repeat that block, how many blocks are there, and that way I can also measure the length, right? So over here we have 5 blocks. So there are many ways to measure length, but we have a standardized unit which we call as a SI system. As per the SI system, the length is actually measured in meters, right? So meters is the SI unit. It is represented by the symbol m. Now remember, this is a unit, right? Do not confuse this with the quantity, which is represented by the symbol m, which is for mass, right? So do not confuse these two. These two are different things. This is a unit symbol and this is a quantity symbol for mass, right? And the unit for mass is actually kilograms. So do not confuse this m with the unit m over here, right? Okay, so measuring length, we can use a ruler, right? A ruler actually has 1 meter in length in total, right? Which is further, you can say, about 100 centimeters. So if we look into the fact of conversion, I can say that for conversion, I'm going to put 1 meter here, right? And I can say, 1 millimeter, right? And milli is actually division by 1,000. So if I want to go from 1 meter to 1 millimeter, I need to divide it by 1,000. Whatever the value I have in millimeters, I need to divide it. Sorry, let me just reshape the arrow. Okay, there we go. So if I want to go from millimeters into meters, I need to divide it by 1,000, and if I want to go from meters into millimeters, I need to multiply this by 1,000, the same amount. Same way, if I want to go from meters into kilometers, right, I need to again divide it by 1,000. Kilo means 1,000, so it would be 1 kilometer. And same way, if I want to convert kilometers into meters, I need to multiply this by 1,000. Now centimeter comes somewhere in between these two actually, so I'm going to put this conversion independently, that 1 meter is equal to 100 centimeters, and centi means 100th of a meter, right? So obviously if it's 1 meter, then there are going to be 100 parts in terms of centimeters, right? Okay, from millimeter I can actually go even further below, in which I have micrometers, right? Now for 1 micrometer, if I want to go into micrometers, I need to multiply this by 1,000 if I'm coming from millimeters, and if I want to go back again, I need to divide it by 1,000. So this is just the basic conversion that you will be needing. I don't think you will need to go any further than micrometers. Nanometers are also there. Again, it's another 1,000th multiple from a micrometer. I'm just going to leave it here because we won't be needing that much smaller units. Now these are bigger units. Now for kilometers or meters, we use a ruler, right? Over here I'm going to use ruler, and for measurement of millimeters, we are going to use a screw gauge, right? Screw gauge is also known as, now I'm going to write it over here at the bottom. right? So a screw gauge uh, is also known as a micrometer. And why it's called a micrometer? Because it can measure up to 0.01 of a millimeter, which is in turn 10 micrometers, right? So if you take the conversion, you will understand that if you multiply this from this rule that we just reviewed right over here, that from millimeter to micrometer, when we go, we need to multiply it by 1000. So if you multiply this 0.01 with 1000, you will get 10 micrometers. So this is 1 micrometer, and this is the smallest measurement this screw gauge can make, right? So I will detail how screw gauge actually works, but for now we're just going to stick to the ruler. So what a ruler is, right? A ruler is basically a straight frame that we have, right? Okay. All right. It starts from 0 and goes all the way to hundredth of a centimeter, which refers to 1 meter in length. Also, it has smaller divisions in it, which are millimeter divisions, right? So it can measure a smaller value of 1 millimeter. It cannot go any lower than 1 millimeter, right? So over here, I'm going to refer this smallest measurement this ruler can take as the least count, right? Now, what is the least count? It is it's the smallest measurement possible by an instrument, right? This is what we call as least count. As the name suggests, is the least count that an instrument, a measuring instrument, can make. For example, if I look into my wristwatch, which is an analog wristwatch, it can measure 1/1 of a second, right? That's the smallest measurement it can take in terms of time, so that would be its least count. When I look into a digital watch, you do know that a digital watch can go beyond that 0/1 of a second. So the least count for a digital watch is actually much more precise than this, right? So this is what we call as the least count. I will further work on this in a moment, what least count truly is and how we can calculate the least count of an instrument, right? But for now, let's stick to the ruler. Now understand, to make any measurement from a ruler, let's say if this is the 0, then we have these small measurements. The fifth one is a bit large, and then again 4, and there we go 1. So if this is 1 centimeter and I have an object which is this big, right? So I need to understand that my viewing should be precisely leveled with this, right? If I view it at a different angle like this or like this, then the measurement is not going to be accurate. So this and this is not the right way to view. So your view should be, your eye should be leveled with the object, making sure that it is precisely with the 0. So how can I ensure that my measurement is accurate? I must use a set square to first set my object precisely. Now in set square, you do know there are several articles that we have. One is a triangle like this, with a isosceles triangle, right? And then I have a right angled triangle, and then I have a protector in there, and then a small little ruler, right? So I'm going to take a ruler and a right angle triangle. I'm going to join these sides so that it becomes a perfect 90-degree angle at this point, and then I must place my object leveled with this, and then take another object or view directly from this. This way I will have the surety that my measurement is accurate. So this is actually a reasoning question asked in the ATP. So it's an ATP based method. I'm going to suggest that use set square to have accurate measurement, right? So accuracy will be better if you're using these set squares to help you keep your objects and measurements to the at a better accuracy level, right? Okay, moving on, we have screw gauge as a second instrument. So as I said, screw gauge. What's a screw gauge? It's actually a device which is shaped like this, right? I'm going to draw a rough sketch of the screw gauge. There's the anvil, there's the screw, and here's are going to be our object. I'm going to make it dark, and then we have this uh, main scale right over here, and then from the main scale we actually have this circular scale. I'm going to label these parts in a moment. Just let me draw this whole diagram first, and there we go, right? So and there's a locking screw. Now the parts of this are not important because there isn't going to be a question about this, but this is what we call as this sorry, let me just correct this. It's not screw, it's called the circular scale, right? This over here is going to have a main line with a 0 on it, right? And some of these smaller lines are also there. So this is what we call as main scale, and this one over here would refer to as circular scale. And circular scale actually has divisions horizontally placed over here, and most of these screw gauges actually have two types of screw gauges which start from 0 to 50, that means 50 divisions, and another one with 0 to 100 division. But most of the time when we have 0 to 50 circular divisions, right, and 0 to 100 circular divisions. So remember, with these two the actually main scale divisions are different, right? For this, the main scale is actually going to have more divisions. For the 50th, the main scale will have 0.5 of a millimeter divisions on main scale. I'm just going to write ms, right? And for this we have 1 millimeter of a division on main scale, right? So if you have either of these two, we are going to find that both of them are going to have a same least count. Now some of these vernier calipers, screw gauges are actually more precise. That means they have much more lower of a least count, but usually these two are available in lab, and these two are the ones that are used in the IGCSE ATP and the experimental questions, right? So how to use that? We use this circular scale, we unscrew this, right, so that we open up these apparent jaws, the anvil, right, and then we place our object, and then we tight it using this tightening screw, right? And once we do that, we need to ensure that we don't tight using this. So this is used for opening and this is used for closing, right? So close using the smaller screw. Why? Because this has a slip screw in it. In case if you try to push or close the object using this one, the main circular scale, it may crush or damage your sample, right? So this will actually starts to slip once you have gently place it. So the first thing would be to have, I'm going to say, gently lock your sample, right? That's the most important part. So you need to gently lock your sample into the screw gauge. Once you do that, you're going to get a main scale reading, right? So what is the main scale reading? That is going to be the line which is barely visible, or the last line that you see over here, right? So I'm going to draw this zoomed up diagram. For example, this is the main scale. From 0 goes to half, 1 millimeter, then half, 0.5. I'm going to use this 50th one, right? So another large one. So this is going to be 1, 2 of a millimeter, and third, and 3, right? Now the fourth is here, but I'm not able to see the fourth line because my circular scale is overlapping that line, right? So I'm just going to just I need some space over here. Right, there we go. Yeah. So once I'm going to draw the circular scale. There's circular divisions. Now I will let you know how to take measurements using the circular divisions, but for now understand this, that if you don't get to see this fourth line, you always take the line prior to it, right? Never assume the next line which is not visible to you. Don't assume that. Always take the line which is in the previous, it's prior to the line which is expected to be here. So if it's the fourth, then don't take the fourth, take it as 3.5, right? So the main scale reading, I'm going to denote it as MSR, is 3.5 millimeters. Since this is in millimeters, the main scale for a screw gauge is in millimeters, right? So that's the main scale reading. Now I need to look at the circular scale, what the circular scale is reading, right? So I'm going to now write the circular scale readout, right? And that is going to be a division number. So as I said, since the circular scale is divided from 0 to 50, I need to see which line from these horizontal ones are perfectly aligned with the main scale central line, which is this central line, right? If it's not perfectly aligned, just the way I drew it, you need to note the previous line. So always take the previous one. If it is not perfectly lined, never take the line ahead of it, right? Okay, so let's say our 23rd division is aligned up, right? It is not lined up properly. The 24th is not, so we're going to take the 23rd, right? So it's the 23rd division. So how I'm going to take the CSR, the circular scale reading, right? That is going to be the number of division multiplied by the least count. Now I haven't found out what least count for my screw gauge is going to be. So least count is actually the smallest. Let me just scroll a little bit. Yeah, the smallest division on main scale divided by total divisions on circular scale, right? And for my screw gauge, the one that I chose, the smallest division was 0.5 of a millimeter, and the total number of divisions was 50. So that is going to give me 0.01 of a millimeter. So that's the smallest measurement which my instrument can make, right? So coming back to the original problem, so what is the CSR? That is going to be actually that's the 23rd division multiplied by the least count. So it is going to be in millimeters. So that is going to be 0.23 millimeters, right? So what is going to be the actual length? The actual length of the object, or the diameter of the ball that we were measuring, is going to be the MSR plus the CSR, right? The main scale reading plus the circular scale reading that we took. Now make this difference that readout means the division and the reading means the actual value in millimeters, right? So this is the reading that we require, not the division. So don't add the divisions over here. So always multiply the division that you find from the circular scale and multiply it with the least count, then get the value in millimeters, and then add it up with the main scale readout. So what is the value for this over here? So that is going to be actually 3.5 plus 0.23. That is going to be 3.73 millimeters. And that's what I meant, that it is not the fourth, right? Not fourth. That is why I did not take the fourth, because the object was a little short than the fourth millimeter reading, but it was greater than 3.5. So the object was somewhere between 3.5 and 4 millimeter. So it must have been somewhere here, right? So understand that micrometer can help you differentiate between such small measurements, right? It can help you take these small measurements, this small difference. If you have measured this object using a ruler, then you would have either taken 3 millimeters or 4 millimeters. And why? Because the least count for a ruler is 1 millimeter. So you cannot have a differentiation between these two, right? There's a whole gap, huge gap in terms of micrometer or the screw gauge between these two digits, right? Which is like from 3.5 to 4 millimeter, right? So this is how you take measurements using screw gauge. Now moving on, we need to understand what precision. Now here, before I go into volume or density or time, I will ensure that we understand that these are the length measurement, and I'm going to conclude this topic over here, as length only refers to the measurement of the distance between 2 points, right? For which over here, for the sample that we were taking, we were measuring the diameter, and using that diameter we can actually calculate other stuff like volume, right? I hope this clarifies the topic. Now we're going to move into volume, right? So what is volume? So volume for us is actually going to be when we talk about volume, so what is volume? It is actually you can say the total space a mass occupies, right? That is what we call volume. And by that we can understand that if I have a box, then its volume is going to be what is the total of this from inside and out, right? So the volume is going to be what is inside this box, the whole space that it is carrying within these boundaries. So that is going to be the volume. So we have several ways to calculate volume. For a cube, the volume is actually if I measure volume for a cube, I'm going to write volume over here. I'm just going to write the name of these objects. So the volume is going to be length into length into length. And why? Because cube is actually having all sides which are equal. So there is no differentiation. So this is L over here, L and L. So the product of all three L's, and that is going to have units in meter cube, right? It's the cube, right? Then we have cuboid, and cuboid is a rectangular shape, so it is going to have length into width into height. So let me draw a cuboid. I'm going to draw a cuboid something like this, so that all three sides apparently are different. So that is going to be the height, this is going to be the width, and this is going to be the length. So again, the unit is going to be meter cube. Then we usually get to work on spheres, right? So for a sphere, we need to understand that sphere is actually a round object. It can be translated into a two-dimensional circle with a certain radius. So when we talk about the volume of a sphere, it is actually 3 by 4 pi r cube, right? That's how we calculate the volume of a sphere, right? Now these are some of these things that we can measure. Then most of the time when we look at some questions, for example, I gave you this question that you need to measure the volume of a swimming pool, right, which is shaped not like any of these that we are working with. And I give you the length of this. Let's say this is 2 meters. I tell you that this is actually 1.5 meters, and the width is again 1.2 meters. So how can I measure the volume of this, considering that the height which is independently given is 1 meter in total? So what is the volume? For this, I need to understand this patch is not available over here, right? This is not available. So what I can do is create a difference between this, which this is going to be 0.5 meter. The difference between these two lengths is going to be this distance. So I'm going to divide it into two portions. One is going to be this portion, right? This is I'm going to call as V2, and this I'm going to call as V1. So I'm going to calculate two independent volumes of cuboids rather than trying to hopelessly work on calculating the collective volume. Instead, I'm going to create a partition and then calculate the volume, for which now I have the length being for V1, it is going to be 1.5 of a length into 1.2 of the width and 1 meter of the height. And for V2, I'm going to have 0.5 of the length, right? And also I need this value over here, this distance, which if I'm given this width, let's say this gap is actually 0.4 meters, right? So that is going to give me a difference of 0.8, right, into the height. So these two volumes I can calculate, and then the total volume Vt is going to be V1 plus V2. So that's how we can calculate the volume of an unknown shaped object by dividing into different partitions into simpler of these versions. We can always divide any irregular shape or into cuboids or cubes, right? So do that, and then you'll be able to calculate the volumes and then simply add up the volumes to get a total volume, right? Now this is a method for fixed shaped objects, but what if I have an irregular shape, right? How can I work on irregular shapes? Let's say this is the object. Now there's no formula which can help you, no formula to calculate, right? No formula to calculate the volume. So now here we have a problem. We cannot use any formula because it's an irregular shape, right? So what we can do is that we use an instrument known by the name of measuring cylinder, right? And what's a measuring cylinder? It's actually an instrument, right, which has it looks more like a pipe which has graduations on it, right? And those graduations are volumetric measurements for liquids. So we actually use measuring cylinder to note volume for liquids, right? And how can we use this to measure the volume of this irregular object? Is that we simply fill this measuring cylinder, right, with some liquid, let's say water, and then note the volume, and we call this as V1, right, or Vi, initial volume, and then we place our object in it. This is the volume without the object in it, and once we put the volume, once we put the object in it, we are going to see a rise in the level of the liquid, and that we are going to call as Vf, right, final volume after placing the object. So the volume of irregular object will be actually the difference from final to initial, right? That is going to be the volume of this. For example, let's say if this was initially we had a reading of 500 ml on the measuring cylinder. Let's say it was a measuring cylinder for 1 liter, and the Vf noted out to be let's say 750 ml, right? The readout was at 750 ml, so it is going to be 750 minus 500. So the volume of this irregular object is going to be 250 centimeter cube. Now why I shifted from ml? Because ml is liters is used for liquids, and centimeter cube is used for solid objects, and we do need to understand that 1 ml is actually equal to 1 centimeter cube. So these two are equal to each other, so I can simply write now centimeter cube over here, and that's the volume of an irregular object, right? So this change in volume, the increase in volume, is actually the difference that this object has displaced water, and that displacement of water is translated in the in volumetric change, and that volumetric change is going to provide us the volume of this irregular object. Now over here I'm going to discuss one critical factor regarding the accuracy of measurement. So whenever you try to measure the volume of a liquid, you understand that whenever you look at the liquid surface, you are going to see this curvature over here, this curved view, right? Why it is curved? Because this is due to liquid retention. For this is what we call as meniscus, right? This curvature of liquid in a pipe or a cylinder is what we call as meniscus. And whenever we're taking out readings, you need to understand, you need to see the lower meniscus, right? Lower part of the meniscus to get your volumetric reading. You're not going to read this upper part. Never read this. And remember, your angle of view should be perfectly aligned, that is accurate. Do not view it from any other angle. So your eye again should be perfectly aligned with the lower meniscus. You should look at it in a parallel way so that you get the right value of volume from these graduations, right? This is the most important part. This will help you improve accuracy, right? So you will get to have several reasoning questions or MCQs. This idea is actually used in MCQs, right? Even in theory paper, paper 4, paper 2, 1, 2 again, 3, 4, and then for ATP as well, right? So there's a reasoning question that how can you improve if the student is looking from this or this angle. They should be looking right at the lower meniscus in a parallel way. That's how they're going to get the perfect volumetric measurement, right? Now this is the part of the volumetric measurement. Now we're going to go into our next topic, which is density of an object, right? So what is density? Density we can denote by the fact that how dense or how heavier an object could get, right? So density, what is density? From here I'm going to just say density is actually how much mass is spread over how much volume, right? That is density. So I denote it is noted by this symbol rho, and for volume we have so for mass we have m, for volume we have capital V. So if we have units, we are going to have kilogram over meter cube, or we're going to have gram over centimeter cube. This is for lab, and this is for actually larger objects. For lab work we use gram per centimeter cube for smaller measurements, and kilogram per meter cube if we're dealing with large masses or large volumes, right? So this is what density is, and what density is going to be. Let's say if I have this a sample in which these are the atoms which are there, the particles, right? So how many particles are there in a given volume? That is what density is. So if I have these two objects which are pretty much similar in volume, hopefully they look alike, although they don't, but let me just try to make a similar size of the object. Okay, let's say these two are having same volume, but except this one only has fewer atoms. So which one is denser? This one is denser and this one is lighter, right? So this is lighter in other words, and this is going to be heavier. Why? Because it is having more mass in the same confinement of volume compared to this, right? So if this was A and B, which one is denser? A is denser. And which one is less dense? B is actually less dense, right? So I'm going to say this is less dense and this is more dense, right? So I think you have a brief idea of what density is, but how questions are asked, we need to understand that some of the ATP questions or theory-based questions, they refer to density calculation of unknown objects. For example, in the case of volume, we had this irregular object which gave us some volumetric change, right? It's in a liquid, it's a mating cylinder that we're using. What we're going to do is that we're going to place this mating cylinder. Now I'm going to start off with the basic steps. I'm going to remove this, right? I'm going to remove, let me just follow the whole steps. So let's say you have a digital balance, right? You place your mating cylinder on it, right? And it will give you certain reading for this empty cylinder, right? Now we don't want the weight of the cylinder or the mass of the cylinder, so we're not going to participate that. So we're going to tear it off. So there's a tear button. We're going to press it and it will turn it to 0. It will now not consider the mass of this empty cylinder anymore. Then we fill it with liquid, and you will see that this value over here is going to change. So I'm going to erase this, right? Now there's a certain volume over here, so that is the mass of the liquid. So let's say it is 10 grams, right? So I'm going to note this mass of liquid is equal to 10 grams, right? And then I'm going to note the volume of liquid, right? Let's say that is 25 ml, right? Now I'm going to place my irregular object in it, and now you will see that there's a rise in the volume. So I'm going to note that this was the initial volume, and now over here we have the final volume, right? So when we have the final volume, we're going to put we're going to note also the mass is going to change because I've added more mass into this. So over here the mass is going to change. Let's say it went from this to 20 grams, right? So I'm going to say that the mass increase is 20 grams now, and the volume increase of liquid is now 35 milliliters, right? So from here I'm going to find the change in mass. Delta mass is going to be 20 gram minus 10 gram. That will give me 10 grams of mass, which is the mass of this object now, right? This is the mass. Delta M is going to be this mass, and then I'm going to find the difference of volume. That is going to be 35 ml minus 25 ml, which is going to be 10 ml. So from this, now I've got the volume of the object as well as the mass of the object, right? Using this digital balance, right? Digital balance. Let me just write this digital balance and this mating cylinder, right? So from here I can calculate the density of this object, that is going to be mass over volume, and in this case we have 10 grams of mass divided by 10 ml of volume. I just told you that 1 ml is also equal to centimeter cube, so I'm going to replace this unit from ml to now centimeter cube, because we're talking about a solid object, right? So that is going to be 1 gram per centimeter cube. So this is how you're going to calculate the density of an unknown object, right? Now this question can be asked in several ways. I will post in more sessions about these past paper questions, and hopefully solve most of these problems which are more trickier than this. This is one of the trickier questions, but I've seen one question which is more trickier than this. Some are even simpler than this, in which they simply give you the mass. You don't need to look into the digital balance, and just evaluate the difference of volume and get the density of the object, right? So I'm going to now move on to the next topic, which is time measurement. So what is time? time is actually how much seconds or the clock is moving on, or how much the our earth is moving around the sun. So the actual parameter for time is actually the movement of, let's say, sorry, let me just remove this. So if here's the sun, right, and this is the earth, I'm just going to denote by E. How much time earth takes to complete one revolution around the sun is what we call as 1 year, and that is further divided into days. It takes segments of 24 hours. How many hours? That is actually 365 days, and we do know that one day is equal to 24 hours, right? So what is time? We actually further divide this 24-hour into minutes and then into seconds. So I'm going to just write 1 year is equal to 365 days. That's from where this evaluation of time came into being, and then one day is equal to 24 hours, and 1 hour is equal to 60 minutes, and then 1 minute is equal to 60 seconds, right? So the SI unit for SI unit for time is actually seconds, right? Although it is taken from the movement of the earth, but we actually work with smaller fragments of time, since 1 year is a very large amount of time. So we work in seconds, since we're dealing with smaller fragments of time. So the SI unit that has been finalized by the System International is actually seconds, right? So how can we measure time? We've got actually two ways. We've got clocks that measure the time, or we have stopwatches to measure time, right? So I'm not going to discuss clocks, but I'm going to measure stopwatches. There are two types of stopwatches. One, we have the mechanical ones, right, or also known as analog watches, or analog stopwatches. Then we have the digital ones. So the digital stopwatch is more precise. So I'm going to say this is more precise, as it can read out smaller fragments of time. Compared to this, the analog is less precise, right? So I'm going to let me just scroll up. Yeah, it is less precise. So we usually prefer digital stopwatches in our lab, but analog stopwatches or mechanical stopwatches are also available. These were previously used. Now digital stopwatches rule, because they usually have a precision of 0.01 second, while the mechanical ones barely have a maximum of 0.1, which is a rare find. Usually they have a least count of 1 second, like the chronographs or the tachometers that are available in most of these wristwatches, right? Mechanical wristwatches. Even a digital wristwatch, it has a stopwatch in it, right, by default, and nearly most of them already have these, right? So how can we read timeout? We can simply use a digital digital stopwatch to see when an event starts and when an event ends. So what is time? So event start to event end, whatever the event is, right? The time lapse for this is called time, right? So the time lapse, how much time it took, is what we call as time, and we usually measure it in seconds. It is represented by the symbol T, and it is measured in units of seconds, represented by the symbol S, right? Now time has many applications, since time is the most critical quantity that we use in physics. Let's say for speed, we understand that speed is actually distance over time, right? How much distance an object covers in how much time. Let's say an object moved from point A to point B. So this is the start of an event and this is the end of an event. So the time it took for this length, that is going to be the speed. So as I said, time is actually measured to calculate other quantities as well. These are derived quantities, and these both of these are basically base quantities. So we use these base quantities to calculate or evaluate these derived quantities, right? Like speed, acceleration, force. These quantities we will be looking into in our future sessions, right? So now finally moving into our last topic of this unit, which is the precision and accuracy. And this is the most fun part. I actually use a different strategy to discuss this. So I'm not going to define precision or accuracy. Instead, I'm just going to draw something for you. Let's say we have a target set, right? Or a dartboard, and as you know that the dartboard has maximum points when the darts hit the center, right? The more you get to the inner circle, the more you're going to have this. Now I'm going to draw these three of these dartboards. I'm going to change the color from here, right? Let's say one dart hit here for this one session, other hit here, next one hit here, one hit the center, and the other also hit closer to the center. So this, I will say, is accurate, right? But not precise, right? I will define these in a moment, but for now let's look into this diagram. Right now another player comes out and he shoots out these darts. So he's not able to hit the center, but he's able to maintain the closeness between the darts. So this, I'm going to say, this is precise but not accurate, right? Another third player, let's say he's a pro player and he's a dart champion, so he's going to hit the darts like this, right? He's able to put nearly all the 5 darts right to the closer to the center. So we're going to say this is both now accurate and precise. So what is accuracy and precision? So I'm going to now define this. So what is accuracy, right? Accuracy is actually the ability to hit the target, right? And what is going to be precision for me, considering this dartboard example, and I'm only defining this using this dartboard right now. I'm not defining this in terms of purely physics. I'm just defining this what accuracy and precision is supposed to be, and then we can change our definitions depending what kind of instrument or object we're trying to measure the accuracy or the precision for, right? So precision, I'm going to define in an entirely different way, that this is actually the closeness of values to each other. Now I'm just going to define it with physics, right? I'm just going to rewrite that to each other. How closer that each of these values were to each other, irrespective of the fact whether they were close to the requirement or not, right? In this case, this was not. In this case, in the third case, they were also close to the target value, right? So I'm just going to, as I said, redefine this. I'm going to say the same way to define this, right? Okay, now what is accuracy? The closeness of values to given target, right? So how close you're able to your target, that is what we call as accuracy. It may not be precise, and then the closeness of values to each other is known as precision, right? But for an instrument, precision is actually defined in a different way. So precision is also defined for, let's say, for an instrument. I'm just going to change the color from this to this, as this is a different definition now, right? So precision can also be defined as the smallest reading an instrument can read, right? So uh, that is also the least count, as we have referred to this. So in for case of uh, instruments, right, we're going to define precision as the smallest possible reading that an instrument can read, also known as the least count, right? So that is the precision, and accuracy would be how well. ठीक है, let me just get over here. Yeah, how well one can read the instrument, right? To avoid any errors, or uh, or avoid errors in reading. So that's the alternate way of defining, uh, you know, accuracy. So since at times it's not necessarily that it is a human error that is involved in the reading. It could be an instrumental error or systematic error or a random error. So that affects the accuracy of your reading, right? So how well one can read the instrument or avoid errors in reading, that is also accuracy, right? I hope I'm able to go through this first unit of measurement, which comprises of these 5 subtopics. Thank you for time. I'll post up other videos regarding the next subsequent topics. Thank you.